Authored by veteran chemistry teacher Abdul Shakur, these two textbooks provide all the essentials that would not only enable students to master grade 11 chemistry, but to excel at the next higher level in this subject. What make these texts unique are their creativity and profundity with which concepts are explained for clarity and mastery. The following is one of a set of 44 different tutorials created by the author, using materials primarily from the text Chemistry 11 in Focus. I hope you enjoyed this video. If you liked it, please give it a thumbs up and don't forget to subscribe. We will see you in the next video and thank you for watching.
Our next lesson today starts on page 33 and it ends on page 37 from the text Chemistry 11 in Focus, and it deals with the following concepts. First, ionization energy trends, electron affinity, and atomic orbitals and subshells. This graph that you see in here is a plot of the first ionization energies of the elements in the first 5 periods of the periodic table here. We will analyze the ionization energy for each of these and to try to explain why there are certain deviations in the pattern. So you can see here, I circled these boron, there's a slight deviation in that. One would is expected to go up, and the same thing with oxygen here, and aluminum here. So what we'll do here is this. We're going to look at the ionization energy and to give an explanation as to why we have that value. We start with hydrogen here, and you can see that it has that value here in kilojoules per mole, right? Helium is bigger than hydrogen, has a greater first ionization energy than hydrogen because of two reasons. One, it has a bigger nuclear charge, and it also involves breaking the duplex. Remember, helium has 2 electrons only in its outer shell. So that is why it has a bigger first ionization energy than hydrogen. Lithium, of course, is less than hydrogen because lithium has an extra electron. So helium has 2 electrons in the first shell, but now lithium has 1 electron in the L shell. So that electron is farther away from the nucleus, and therefore it entails less energy to remove it than what helium needs. Beryllium has a higher first ionization energy than lithium because it has a greater nuclear charge, and therefore it's holding on to electron more strongly than lithium does. But look what happens here. Boron has a greater nuclear charge than beryllium, yet it has a smaller first ionization than beryllium. That is something we look into. Because if you remember, beryllium, boron, carbon, nitrogen, fluorine, as you move from left to right of a period, the effective nuclear charge increases and the atomic radius decreases. And therefore, as you move from left to right, one would expect that the first ionization energy will keep increasing. But this is not what happens here. There's a slight deviation here. Same thing here for oxygen. And here you have the same thing for aluminum. One would expect aluminum to have a higher first ionization energy than magnesium. So let's look at these values here again. So this is where the deviation comes on. One would have expected boron to have a greater first ionization energy than beryllium. And then here again, oxygen, we expected oxygen to be greater than nitrogen. So we'll try to see why that is happening. For us to understand why that, we need to introduce a new concept, the concept of atomic orbitals and subshells. You know, going back to the Bohr atom, you know, the Bohr model of the atom works only for the hydrogen atom, since it could not explain the line spectra produced by atoms with more than 1 electron. To explain these anomalies, scientists have put forward the theory of atoms having orbitals. An orbital is a volume of space on or about the nucleus of an atom where there is a possibility of finding an electron. Now let us look at helium here, for example. Helium has 2 electrons in its first shell. What scientists are saying is that the electrons are not moving around the nucleus in a circular way, but this entire shell here is really an orbital. So you can imagine this as being a spherical piece of styrofoam, and that will represent the K shell. Now they name these orbitals, they will call this an S orbital. And because it is found in the K shell, is the first set of orbital that's spherical like that, it is called a 1s orbital. Hydrogen and helium will have a 1s orbital because they are found in this K shell. Let us say you have an atom here that has a K shell and an L shell. We can remove these into 2 different shells. Separate the K shell here, we get this one here, just like what we had here. But this one here now is what we have here. So what scientists have found is that this here can be broken down into 2 subshells. This one here can be broken down into this subshell here, which is called a 2s orbital, and 3 dumbbell-shaped orbitals that we'll call the p orbitals. Electrons here are slightly different from each other. 6 electrons will have energies that are higher than 2 of them. So the theory is that, look, we are having another subshell here that is spherical, but it is bigger than the subshell here in the first shell. So in the second shell, we are having 2 types of orbitals. We are having a spherical orbital that we call the 2s orbital, not in terms of number, but in terms of position. So you see, this first one here is found in the K shell, and this one here is found in the L shell. And also these ones here are there too. So you have 3 of these and 1 of this. But these guys here are not arranged like this. They have an arrangement as depicted by the figures above, where one is lying on the x-axis and the other 2 are lying on the y and z axes respectively, mutually at 90 degrees to each other. So if one were to put all of these here together, let's suppose this was a styrofoam ball here, and this was a bigger one. This 1s has a nucleus with it. Imagine now we drill a hole into that and we place that inside there. So we'll have a bigger styrofoam ball, but in the center of that, we have this orbital here, the 1s orbital. Now you can see that we can place these around here. You can't show it like that. So one is going here, perpendicular like this. One is passing through like that in the horizontal way, and that one is going to the other axis there. So this is how we can envision how these 4 orbitals are arranged. Atoms of helium and hydrogen will only have 1s orbitals. But as the atoms gain more and more electrons, like lithium for example, lithium will have exactly what this one has, plus it will have another electron that will be found inside here. Beryllium, same thing, but 2 electrons. Boron, same thing here, 3 electrons. Carbon 4, nitrogen 5, oxygen 6, fluorine 7, and neon will have this octet there. These orbitals here will be related to these atoms here, and not hydrogen or helium because they only have 1 and 2 electrons respectively. Let's say we have a bigger element. Let's say this is argon. Let's say this is the Bohr-Rutherford diagram from argon. If we remove all of these shells separately, we're going to have a K shell here. This one, like we did before, will be the L shell. And this one here becomes the M shell. Argon here will have everything that helium had, everything that neon had, and it will have 8 more electrons outside there. Any element that has more electrons than neon, say sodium for example, sodium has 11 electrons. The 2 will come in this one, 8 here, and 1 will go in this other shell here. So like that, it shall become progressively filled until you meet argon, and then argon is going to have this here. So argon will have 2, 8, 8. Just like how we have this shell here, L shell, has 2 sets of orbitals. The M shell also has 2 different sets of orbitals. It has a bigger s orbital that we'll call it 3s orbital. And 3 dumbbell set of orbitals, we'll call that the 3p orbitals. Not in number, but in position. So this is called the 1s orbital, spherical. This is called the 2s orbital because it's in the second shell. That's called the 3s orbital because it's in the third shell. And note how progressively bigger and bigger these s orbitals get. Same thing with the p. There's a 2p orbital here, and the 3p orbitals are bigger than those. How do we put all of these together? How are these arranged around the nucleus of an atom? Let us dismember this. So here is the 1s orbital. We can now place this behind that one there, look. Okay? But really not placed behind. This one is inside. This 1s is inside of that. This guy here can come here now. Let's put that there. Now I want you to see how the 2p orbitals are farther away from the nucleus than the 2s orbital. And you should know that the farther away the electrons are from the nucleus, the more energy they have. In this case, the electrons in the 1s orbital will have the least energy because they're held strongly by the nucleus here. This one will have more energy than the 1s because they're farther away. And these ones here, in all these here, they'll have more energy than any of these here. This 3s orbital, put it here, but note now, it envelopes everything. So we can take all of these 3 orbitals here and fit it inside 3s. So if you put that inside the 3s, let's say that was another big styrofoam ball, you wouldn't see anything. This is these here in the center of that styrofoam ball. You wouldn't see anything if you close it up. You take this guy now, same thing. These are arranged neutrally at 90 degrees to each other. And you put it like this, behind there now, not behind, they're really going in between all these here, right? So now the 3p orbitals will have more energy than those. In grade 12 chemistry, you'll do what is called the Aufbau's principle. When you try to put electrons into these orbitals here, you'll have to start by putting the electrons in the one that has the least energy, because even if you put one electron there before you fill the shell, it will automatically come inside because the nucleus will just pull it in. So you fill in this 1s, then the 2s, then the 2p, then the 3s, then the 3p. That will help us to understand why we have these deviations in the first ionization energy. So we can have another look at this one here. Nicer than the one. Now, same thing we have here, a little bit more, some more details you've seen here. Look at this. Here is the 1s orbital, the K shell, 1s orbital. So what we do, we represent orbitals with circles here, and 2 electrons will fill this one here. This is helium. It has only 2 electrons, and that is in the K shell here, right? And this is how the orbital is here. This one here is neon. Neon will have exactly what helium has. It will have this one. In addition to that, it will have the electrons in this second shell here, and this second shell here will have an s orbital here. This is and that is spherical in nature here, and 2 electrons will be inside there, along with 3p orbitals here. Later on, you see, we'll call this py, 2px, 2py, 2pz, and that is the L shell here. Now taking these, you can put these like that. This is how the orbitals in the second shell will be arranged. Let's say you have argon now. Argon will have a 1s here, which is spherical, okay? It will have a 2s one here, plus you'll have all of these two. In addition, this last M shell will have a 3s orbital and 3p orbitals. And put all of these orbitals here, you'll have these. So what happens if you take these, take this one, and you put it inside that one, this is the 1s, it'll be in the center there, and then you take this guy, envelope all of this here, and then you have all of these fit together inside a nice spherical shape there, and that is how you're going to get all these orbitals. But the important point to know is this. As you move away from the nucleus, the energy of the electron in these orbitals get more and more and more. So let us see how we can use this concept of subshells and atomic orbitals to explain why we have these deviations here. If you can remember in the previous video, when you move across a period, the effective nuclear charge increases in that direction, and the atomic radius decreases like that too. Boron is here, and it has a smaller force ionization energy than beryllium. One would expect as you move in that direction, because of greater nuclear charge and a smaller atomic radius here, one would expect to remove an electron from this one here will take more energy than this one here. So let us compare these two. Let's see how they fill in these orbitals there. You get in a nice little peek into grade 12 chemistry. Let us do an energy level diagram of beryllium. So beryllium will, first of all, the 2 electrons will come inside this 1s here. You have to fill the 1s first. And 2 electrons that will go into this 2s orbital there. That's beryllium, right? 2 and 2. Boron has 5 electrons. So boron will have what beryllium has in addition to that, an extra electron. Now if you take this electron here and put it here, look what is happening. You see, according to the Bohr diagram, it will appear as if all these are in the same orbit, right? But this one is in a higher subshell. And this is farther away from the nucleus. So this outer electron here, let's say the nucleus was there for beryllium, right? Beryllium is holding on to this guy like this. But look what happens. In spite of the fact that boron has a nuclear charge of 3, because that one electron is a subshell farther away, it's easier to remove that one there from boron than to remove that one there from the beryllium. So that explains why there is a deviation in boron. Now look at oxygen. We will expect oxygen to be higher than nitrogen, but oxygen is less. Oxygen on the right should be more because of greater nuclear charge, but it's less. Let's do nitrogen and then do oxygen here. Let's fill in the number of electrons here. So nitrogen has 7. This is 4. So when you do these things, you will learn something called Hund's rule. Don't double them up yet, right? So this is what? That is nitrogen. Oxygen has 8 electrons. So we need to put on 1 more electron. So we need to fill this subshell here before you go into another shell. This is the K, this is the L shell here. Sorry, every orbital can only hold 2 electrons. I forgot to tell you that. Put in 1 more there for oxygen. You're going to have something like this here. Look. Another electron coming there. So what is happening now? This extra electron here for oxygen causes greater electron-electron repulsion there now. See? That extra electron there is creating some stress for these electrons here, and therefore it is easier to remove one of those electrons there now from the oxygen atom than from the nitrogen atom because of the greater electron-electron repulsion there. Same thing for aluminum too. Same thing you can do for aluminum. Aluminum is less than magnesium. Aluminum is to the right of magnesium in a row, and you expect it to have a greater force ionization energy. So let's look at magnesium. Now we fill this one here. An electron will be removed from this 2s orbital for magnesium, right? And it requires some amount of energy. If I have aluminum now, you need another electron. And this electron here will be in the 3p orbital here. See that? Now this one here, because farther away from the nucleus, it requires less energy than this guy here. And that is why you have all these minor deviations. So I hope you understand that quickly. 1.2, you should note, atomic radius for oxygen is greater than that for nitrogen. Now that I've given you the answer, I want you to figure it out. It's supposed to get less. It has to do with that extra electron that goes into a higher subshell. So I hope you understand the concept of atomic orbitals and subshells.